Across the dark fabric of the observable universe, matter is not distributed evenly, but is instead woven into a vast and intricate structure, a cosmic web of filaments and voids sculpted by gravity over 13 billion years of expansion and cooling. Great rivers of dark matter, traced by the faint light of countless galaxies, flow across hundreds of millions of light-years, converging upon intersections of unimaginable density. These nodes, the grandest gravitationally bound structures in the cosmos, are the galaxy clusters, congregations of hundreds or even thousands of galaxies, all orbiting a common center of mass. They are islands of extreme activity, permeated by a tenuous, superheated gas visible only in the X-ray spectrum, a medium hotter than the core of any star. Within one such cosmic intersection, located at a distance that requires its light 57 billion years to reach us, lies a structure of exceptional character, the Phoenix Cluster. It is an object of superlatives, a place where the normal, sedate processes of cosmic evolution have been amplified to a violent and brilliant extreme. At its very heart, within the central dominant galaxy, there exists a gravitational singularity, a black hole of such profound mass that it challenges the known models of cosmic formation. Designated Phoenix A, this object is estimated to contain the mass of 100 billion suns, a figure that places it in a rarefied class of ultramassive black holes, entities whose existence pushes the boundaries of theoretical astrophysics. It is not merely a static monument to gravitational collapse, it is an active engine, a furnace of creation and destruction whose influence extends across its entire galactic host and far out into the intergalactic medium, shaping the destiny of its entire cluster in a constant, roiling battle between gravity's inward pull and energy's outward thrust. The environment that hosts this titan is a crucible of cosmic extremes. The Phoenix Cluster, formerly known as SPTCLJ 2344-4243, is itself a record holder, one of the most X-ray luminous and massive clusters ever discovered. The space between its constituent galaxies is not empty but is filled with the intracluster medium, a vast reservoir of baryonic matter containing more mass than all the cluster's stars combined. This gas is heated to temperatures exceeding 100 million Kelvin, stripped of its electrons and glowing fiercely in high-energy X-ray light. In a typical massive cluster, the immense gravitational pull of the central galaxy and its dark matter halo should cause this superheated gas to cool over cosmic timescales. As the gas radiates its energy away, it should lose pressure support, causing it to sink slowly toward the cluster's core in a process known as a cooling flow. This inflow of cool gas would then provide the raw fuel for a burst of prolific star formation. For decades, however, astronomers observed a discrepancy. In most clusters, this predicted deluge of star birth was absent. The cooling flows appeared to be suppressed, quenched by some unknown heating mechanism that kept the gas hot and diffuse. The leading candidate for this cosmic thermostat has long been the supermassive black hole at the cluster's center, which, through its energetic outbursts, injects enough energy back into the intracluster medium to prevent catastrophic cooling. The Phoenix Cluster, however, presents a stark and brilliant exception to this rule. Here, the cooling flow is proceeding with astonishing vigor. Observations indicate that gas is cooling and condensing out of the intracluster medium at a rate of thousands of solar masses per year, feeding the central galaxy with an unprecedented torrent of fuel. This has triggered a colossal starburst, with new stars forming at a rate of approximately 740 solar masses annually, a rate hundreds of times greater than that of our own Milky Way galaxy. The central galaxy of the Phoenix Cluster is not a quiet, red-ended elliptical, but a vibrant, blue, luminous factory of stars, all because the delicate balance between cooling and heating has been dramatically, and perhaps temporarily, broken. At the epicenter of this cosmic maelstrom, Phoenix A acts as both the ultimate cause of the cluster's turmoil and its potential regulator. This 100 billion solar mass object is not dormant, it is actively accreting matter from the immense cooling flow that surrounds it. Gas, drawn from the intracluster medium, spirals inward, forming a vast, flattened structure around the black hole's equator, an accretion disk. As this material orbits closer to the event horizon, gravitational and frictional forces heat it to extraordinary temperatures, causing it to shine with an intensity that defies imagination. The light from this disk, spanning the entire electromagnetic spectrum from radio waves to gamma rays, transforms the galactic nucleus into a quasar, one of the most luminous objects in the universe. The power output of Phoenix A's quasar activity is staggering, releasing energy equivalent to trillions of suns from a region of space no larger than our solar system. This radiant energy, a torrent of photons, pours out into the central galaxy and beyond, creating an immense pressure that pushes back against the infalling gas. This process, known as radiative feedback, is the first line of defense against the cooling flow. It ionizes the surrounding gas, heats it, and can drive powerful winds that clear out the galactic core. Yet, in the Phoenix cluster, the sheer volume of inflowing material is so immense that this radiative pressure alone appears insufficient to halt the cascade. The black hole is being fed at a prodigious rate, growing in mass while simultaneously attempting to starve itself by pushing its own fuel source away. It exists in a state of violent, self-regulating conflict, a gravitational engine engaged in a cosmic tug-of-war, where the very act of consumption generates the force that resists further consumption. The brilliance of its quasar is the visible manifestation of this struggle, a beacon shining across billions of light-years, signaling a fundamental battle between gravity and light at the heart of a galaxy cluster. Beyond the incandescent glare of the accretion disk, Phoenix A unleashes a far more potent and directed form of energy. Not all the material spiraling toward the event horizon is consumed. A fraction of the infalling charged particles becomes ensnared in the black hole's powerful, twisted magnetic fields, which are anchored deep within the churning plasma of the inner accretion disk. Acting like a colossal cosmic accelerator, these magnetic fields channel and accelerate the particles, confining them into two narrow, opposing beams that are ejected from the black hole's poles at velocities approaching the speed of light. These are relativistic jets, phenomena of such extreme physics that they are still not fully understood. They are invisible in optical light but blaze brightly in the radio spectrum, carrying an immense amount of kinetic energy away from the black hole. This kinetic feedback is a far more efficient mechanism for heating the surrounding medium than the diffuse pressure of radiation. While the quasar's light illuminates and warms the gas in its immediate vicinity, the jets act like cosmic drills, punching through the host galaxy and extending for hundreds of thousands of light-years into the intracluster medium. They are coherent structures of immense power, transporting energy from the compact central engine to the vast scales of the cluster. The energy deposited by these jets into the surrounding gas is thought to be the primary mechanism that solves the cooling flow problem in most clusters. The jets inflate huge bubbles of relativistic plasma, stir up turbulence, and generate shock waves that propagate through the gas, providing a distributed heating source that keeps the entire core of the cluster from cooling and forming stars. Phoenix A is undoubtedly producing such jets, but the sheer ferocity of the starburst in its host galaxy suggests that even this powerful kinetic feedback is currently being overwhelmed by the immense cooling flow, or perhaps that the jet activity is cyclical, and we are observing the cluster during a period of relative quiescence between major outbursts. The tangible evidence of this titanic struggle is carved into the very structure of the Phoenix cluster's core, visible to the penetrating gaze of X-ray observatories. Where the relativistic jets from Phoenix A have plowed into the dense, hot intracluster medium, they have excavated vast, cavernous voids. These structures, known as X-ray cavities or radio bubbles, appear as ghostly deficits in the X-ray emission maps of the cluster. They are regions where the hot, X-ray-emitting gas has been physically pushed aside, displaced by the pressure of the relativistic plasma injected by the black hole's jets. The scale of these cavities is breathtaking. They can span hundreds of thousands of light-years, dwarfing the size of entire galaxies. The energy required to inflate such bubbles is colossal, equivalent to the explosive power of billions of supernovae. By measuring the size and pressure of these cavities, astrophysicists can calculate the mechanical power of the jets and thus the total energy output of the black hole over millions of years. In the Perseus cluster, home to a well-studied supermassive black hole, these cavities are prominent and clearly indicate that the central engine has successfully regulated the cooling of the intracluster gas. In the Phoenix cluster, the situation is more complex. Faint cavities have been detected, confirming that Phoenix A is indeed producing powerful jets. However, these cavities appear smaller and less energetic than what would be required to fully offset the observed, extreme cooling rate. This suggests a profound imbalance. The black hole is fighting, carving out these immense voids, but the gravitational pull of the cluster is winning, driving an inflow of gas so powerful that it overwhelms the heating effects. We are witnessing a system pushed to its limits, a cosmic ecosystem where the feedback loop that normally maintains equilibrium has been broken, resulting in the spectacular starburst that gives the cluster its name, a phoenix-like rebirth of stars from the cooling ashes of the intracluster medium. This delicate, and in this case broken, balance between cooling and feedback directly governs the life cycle of the most massive galaxies in the universe. In a typical, mature galaxy cluster, the central black hole's feedback has established a stable equilibrium. The jets and radiation provide just enough heat to counteract the cooling of the intracluster gas, effectively starving the central galaxy of the fuel needed for star formation. This process quenches the galaxy, causing it to cease making new stars and evolve into a red and dead elliptical, populated only by old, red stars. The vast majority of massive central cluster galaxies fit this description, their quiescence a testament to the long-term regulatory power of their central black holes. The Phoenix cluster's central galaxy stands in stark defiance of this paradigm. Its prodigious star formation rate of 740 solar masses per year is not just a statistical outlier, it is a direct challenge to our understanding of galaxy evolution. It demonstrates that the quenching process is not inevitable or permanent. Under the right conditions, namely, an exceptionally massive and dense cluster halo that can drive an overwhelming cooling flow, a central galaxy can be reignited with spectacular fervor. This system serves as a crucial laboratory for understanding the physics of accretion and feedback in the most extreme environments. The question is not whether Phoenix A is powerful, but whether it is powerful enough. The current starburst suggests that for now, it is not. However, this may be a temporary state. The massive inflow of gas that is fueling the starburst is also feeding the black hole itself, causing it to grow in mass and, consequently, in potential power. Over time, as Phoenix A's mass increases, its feedback energy may eventually escalate to a point where it can finally overpower the cooling flow, shutting down the star formation and bringing the cluster into a more typical, quiescent state. We are observing a fleeting moment in a cosmic cycle that plays out over hundreds of millions of years, a dynamic interplay between inflow and outflow that dictates the fate of galaxies. The immense figure of 100 billion solar masses attached to Phoenix A is not a direct measurement, but an estimate derived from indirect evidence, a number that emerges from the subtle gravitational influences the black hole exerts on its surroundings. Directly imaging the shadow of such a distant object is beyond the capability of current technology. Instead, astronomers rely on scaling relations that connect a black hole's mass to the observable properties of its host galaxy. One of the most robust of these is the m-sigma relation, which correlates the black hole's mass, m, with the velocity dispersion, sigma, of the stars in the galaxy's central bulge. A more massive black hole creates a deeper gravitational well, causing the stars orbiting near it to move at higher average speeds. By measuring the Doppler shift in the light from these stars, astronomers can calculate their velocity dispersion and, from that, infer the mass of the central object required to bind them. For Phoenix A, this method is complicated by the extreme distance and the obscuring dust and gas from the ongoing starburst. The estimate of 100 billion solar masses comes from combining these stellar velocity measurements with observations of the motion of gas in the galaxy's nucleus and the energy required to inflate the observed X-ray cavities. It represents an upper limit, with other analyses suggesting a mass closer to several tens of billions of solar masses. Even at the lower end of this range, however, Phoenix A remains a true behemoth, an ultramassive black hole that strains our models of formation. A black hole of this magnitude would possess a Schwarzschild radius, the boundary of its event horizon, of nearly 600 billion kilometers, a diameter more than 100 times the distance from the Sun to Neptune. It is a region of spacetime so severely warped that it constitutes a gravitational entity larger than many star systems, a silent, invisible abyss whose presence is betrayed only by the furious activity it ignites at its edge and the subtle dance of stars it commands from afar. The very existence of an object as massive as Phoenix is so early in the universe's history, we see it as it was 57 billion years ago, when the cosmos was only about 8 billion years old, poses a profound cosmological puzzle. How do such giants form? The standard model of supermassive black hole growth is hierarchical. It begins with smaller, seed, black holes, with masses perhaps a few hundred times that of the Sun, formed from the collapse of the first generation of massive stars. Over cosmic time, as their host galaxies merge, these seed black holes sink to the center of the newly formed, larger galaxy, where they eventually merge with each other. Through a long sequence of such mergers, accompanied by steady accretion of gas, a supermassive black hole gradually builds its mass. While this model successfully explains the formation of black holes up to a few billion solar masses, it struggles to account for the rapid emergence of ultramassive objects like Phoenix A. The timescales are challenging. There may not have been enough time for a sufficient number of mergers to occur. Furthermore, each merger event can impart a gravitational kick to the resulting black hole, potentially ejecting it from the galactic center and interrupting its growth. This has led to the development of alternative theories, chief among them the direct collapse model. In this scenario, a massive primordial cloud of hydrogen and helium gas in the early universe, with a mass of 100,000 solar masses or more, collapses under its own gravity. If the conditions are right, specifically, if the gas cannot cool efficiently enough to fragment and form stars, the entire cloud can collapse directly into a single, massive black hole seed. This process bypasses the slow, star-based formation route and provides a significant head start, creating a seed that is already supermassive. The existence of Phoenix A, and other recently discovered ultramassive black holes, provides compelling circumstantial evidence that this more exotic, direct collapse pathway may be a crucial, if rare, component in the cosmic story of black hole formation, a mechanism required to forge the true giants of the universe. Regardless of how its initial seed was formed, for Phoenix A to reach its current estimated mass, it must have undergone a prolonged period of exceptionally rapid accretion. There is a fundamental physical limit, however, on how fast a black hole can grow by consuming gas. As material falls into the accretion disk and heats up, it radiates energy outward. This outward flow of photons exerts a pressure on the infalling gas, pushing it away. The Eddington limit defines the theoretical maximum luminosity an accreting object can achieve before this radiation pressure becomes so strong that it halts any further accretion, effectively choking off the black hole's fuel supply. For a black hole to grow significantly, its accretion rate must be carefully balanced at or below this limit. To explain the immense mass of Phoenix A, it must have spent a significant portion of its life accreting at or, paradoxically, even above the Eddington limit. Such super-Eddington accretion is a frontier of theoretical astrophysics. Models suggest that it might be possible if the accretion disk becomes geometrically thick and puffy. In this state, much of the radiation produced deep within the disk becomes trapped and is advected inward with the gas flow, rather than escaping to push back against the incoming fuel. This radiatively inefficient accretion flow would allow the black hole to consume matter at a much higher rate than the classical Eddington limit would permit. The Phoenix cluster, with its immense cooling flow providing a virtually inexhaustible fuel source, presents a perfect natural laboratory for studying this extreme accretion regime. The ongoing starburst and the sheer scale of the central object suggest that we are witnessing a system operating in this very state, a black hole feasting at a rate that defies conventional limits, growing at a pace dictated not by the gentle push of light, but by the overwhelming, brute force of gravity in one of the densest regions of the universe. Returning to the grand cosmic scale, the Phoenix cluster and its central titan are not merely isolated curiosities, they are a window into the past, a snapshot of a more violent and formative epoch in the universe's history. The light we receive from it today began its journey 57 billion years ago, when our own Sun and Earth were just beginning to form. We are seeing the cluster not as it is, but as it was, during a phase of its evolution characterized by extreme activity. What has become of it in the intervening eons? Has Phoenix A, fattened by the very cooling flow it battles, finally grown powerful enough to win the war? Have its jets now swelled to such a size and power that they have successfully quenched the starburst, heated the intracluster medium, and brought the central galaxy into the quiescent state typical of its peers? Or has the cooling flow persisted, perhaps even leading to further mergers with other galaxies in the cluster, potentially swelling the central black hole to even more incomprehensible masses? The answers lie frozen in time, carried by light that has not yet reached us. Phoenix A stands as a monument to the dynamic and cyclical nature of the cosmos, where the processes of creation and destruction are locked in a perpetual dance. The gas that cools from the intracluster medium forms stars, and those stars, at the end of their lives, return their material to the interstellar medium. Some of that material is then funneled toward the central black hole, which, in turn, releases energy that shapes the fate of the entire system. It is a vast, interconnected feedback loop playing out over scales of millions of light-years and billions of years. Within this system, an object of 100 billion solar masses, a gravitational singularity that warps spacetime on a scale larger than our solar system, is but a single component, a critical node in a web of cause and effect, a silent engine whose existence is a testament to the inexorable power of gravity to assemble matter into structures of ever greater complexity and grandeur, all unfolding in the silent, patient depths of cosmic time.